and welcome to today's lecture on ATM. In the last lecture, we have discussed about two important packet switch network, X.25 and frame relay. In this lecture, we shall discuss about another very important packet switch network, that is your ATM. In fact, ATM is the most popular packet switch network of today. Let us see the outline of today's talk. First, I shall discuss about the need for ATM, what is the requirement for ATM. Then the one very important concept that is being used in ATM, that is cell switching. I shall elaborate on the concept of cell switching. Then I shall focus on ATM architecture, and as we shall see, ATM is based on virtual circuit connections. We shall discuss how virtual circuits are set up, or what are the different types of virtual circuits used in ATM, and also we shall discuss about the switching types used in ATM, and the physical layer device, that is the switching fabric used in ATM, also we shall discuss that. Then as we shall see, ATM has got three different layers: physical, ATM and AAL. We shall discuss about these three functions of these three layers in detail. And on completion, the students will be able to understand the need for ATM. They will be able to explain the concept of cell switching. They will understand the architecture of ATM. They will be able to explain the operation of virtual connections and switching types used in ATM, and they will be able to explain the function of switching fabric of ATM, and again, as I mentioned, they will be able to explain the functions of the three ATM layers, the physical, ATM and ALL. So, let us start with the need for ATM. If we look at the existing technologies, you will find that it has got several limitations. First one is the different protocols uses different frame sizes. The size of the frames can be small, can be large. In other words, the frame size is variable, and for complex networks, information carried in the header is extensive, leading to inefficiency. That means the information carried in the header is quite big and it contains lots of information, and as we know, bigger the header, it is essentially an overhead on the network. So, a bigger header leads to higher overhead, and this leads to inefficiency. To reduce inefficiency, the size of the data field is increased or it is made variable, as I have mentioned. Now, variety of frame sizes makes traffic unpredictable and inconsistent data rate delivery. That means, whenever the frame sizes are different, then as we shall see in with the help of a diagram, it will make the data traffic unpredictable. When a particular frame will reach, how long it will take, what will be the delay, all these things become unpredictable, and as a result, data rate delivery cannot be ensured. And as we know, TDM is time division multiplexing is commonly used to make use of the broadband technology, because the transmission media that is being used has higher bandwidth. We would like to make use of the broadband technology, and for that purpose time division multiplexing is commonly used. And ATM technology has been developed to overcome some of the limitations that I have already mentioned. And the most important features, design features of ATM are mentioned here. First of all, it makes use of the high bandwidth transmission media which has lesser probability of error. Most of the earlier protocols, for example, X.25 and frame relay, uses transmission media of lesser bandwidth, for example, twisted pair or coaxial cable. On the other hand, ATM uses optical fiber. In other words, nowadays optical fiber is the most popular transmission media available today. and that, as you know, that optical fiber has got very high bandwidth and the probability of error is much reduced. So, that means the frames that are transmitted through the transmission media is less prone to error. So, we have to exploit these two features in ATM. That is one design goal. And interfacing capability with the existing systems. Obviously, whenever we go for new technology having high bandwidth, low data rate, I mean low error probability, we have to also be able to use the interface with the existing systems, so that the data coming from the existing systems can be transported through ATM. And also it is necessary to have cost effective implementation. And as I have already discussed in detail earlier, that our telecom industry uses some hierarchies like T1, T2, T3 and so on. So, the ATM should support these hierarchies. That was one of the design features. And as we know, the most of the circuits are circuit switched. For example, our public telephone system is circuit switched. On the other hand, the circuit switch network has got a number of limitations. That is why it is essential to have packet switch network. However, it should be connection oriented. That means it must be based on virtual circuit switching concept to ensure accuracy and predictability, which cannot be ensured by datagram technique, and more functionality in hardware than software for higher speed. And it is also one of the design goal was that most of the functionalities will be implemented with the help of hardware rather than software, so that it is fast and can be implemented with lower cost. Let us look at the limitations of the variable size frame multiplexing. So, here we see that in the present day technology, the frames are of variable size. So, whenever there is a big frame in front of a small frame, this for example, A is a much bigger frame than the B1 or C1, and because A takes quite long time to for transmission, for propagation to go through the medium, the B1 will suffer. It will suffer because it will suffer much longer delay. That means different frame sizes make traffic unpredictable, as I have already mentioned, and data rate delivery can vary dramatically. This cannot be tolerated by real time traffic, for example, video, voice, whenever it is communicated, this cannot be tolerated. For example, audio and video frames are moreover, as we shall see, the frames used by audio and video are smaller in size. So, the present day technology, that means X.25 or frame relay, does not really exploits this very small size of the audio and video frames. So, these limitations are overcome by using cell switching. So, cell is considered to be a fixed size block of information. So, fixed size, so it is not a variable size, and usually the size is very small. For example, in ATM, as we shall see, the size of the cell is only 53 bytes, and all the frames are of the same size, and the cell is used at the basic unit of data exchange. And also ATM uses asynchronous time division multiplexing. We have already discussed about the limitations of synchronous time division multiplexing and how asynchronous time division multiplexing overcomes the limitations we have already discussed, and that is being used in ATM. So, here we see the frames, these are the various cells coming from different sources, and because of asynchronous time division multiplexing, as you can see, first A1, then C1, then A2, they do not have the fixed slots, and as a consequence these cells will be will go in different, I mean the order is different in different frames, and so because of asynchronous communication. However, because of because of high speed and smaller frame size, the cells coming from different sources will reach the destination much more quickly. So, these are the advantages. In spite of interleaving, none suffers long delay. We have seen in the previous slide, you see there is some interleaving, A1, then C1, then A2, then B1, then D1, then A2. For example, A1 and then A2 is appearing somewhere here. In between, you have got several other cells. In spite of this interleaving, the none suffers long delay because of high speed and also because of small cell size. A particular link cannot monopolize the medium, and as a result none suffers long delay, and cells reach different destination in the form of continuous stream because of high speed and small size of cells. That means the data frames or video frames coming from different sources will reach the destination in the form of continuous cells, continuous stream of cells, and they will reach with much less delay, and as a consequence it will be possible to support this kind of real time traffic. So, switching and multiplexing by hardware at the cell level makes implementation inexpensive and faster. So, I should add and faster. So, this is the basic advantages of cell switching. However, there are some limitations. For example, although since the cell size is small, and as we shall see, header has got 5 bytes and the payload is 48 bytes. So, that makes this is the size of a cell, and as a consequence the overhead is 9.4%, that is quite high. So, ATM has got high overhead in terms of header, because of bigger header relative to the size of the cell, but the advantages actually is more than the limitations that is being imposed by this large overhead, as we shall see. And also it has got different types of delays. For example, packetization delay at the source. For example, data is coming from audio sources. So, they will be packetized in the form of cells. Since the audio data will arrive at a smaller rate, there will be some delay in packetization, in making the packets. This is known as PD delay, packetization delay at the source. Then the transmission and propagation delay. Whenever you are sending over a long communication media, if the distance is very long, as you know, there will be some propagation delay, and that propagation delay is usually relatively higher compared to the transmission delay. Because of smaller frame size, the transmission time will not be small because the speed is high. It is about 155 megabits per second. As a result, to transmit 54 bytes will not take long time. However, the propagation time can be quite long, and these two are added where this propagation time is more significant than the transmission time, and this time is known as the TD or transmission delay, although the propagation time is more significant. Then the queuing delay at each switch. So, whenever the packets arrive at a switch, several such packets may arrive from different sources simultaneously. As a result, there will be some delay in serializing or queuing the packets. So, that will lead to some delay. This is known as QD. So, QD is another, and then fixed processing delay at each switch. You know that the switches will take some time, as we shall see, for the purpose of error checking and synchronization, and this processing delay at each switch will lead to some delay. And finally, the jitter compensation or depacketization delay at the destination. Since the packets are arriving with different delays, it is necessary to buffer them. For example, when you are playing a audio cassette, audio or data, or you are playing a video, then it is necessary to buffer them, then send at continuous rate, and that leads to the depacketization delay, so that the jitter compensation can be done at the destination. So, you see that the whenever a packet passes through the ATM network, different kinds of delays are suffered by it, but these have to be taken into consideration in designing the network. And this can be we have the proper by proper architecture and design. Let us look at the ATM architecture. Here, as you can see, these are the user interfaces. These are the user interfaces, and this is your ATM network, where you have got a number of ATM switches, and this interface between the user and the switch is known as user to network interface. So, these are all user to network interfaces, and here these are all user to network interfaces. On the other hand, the interfaces between a pair of switches between pair of switches is known as network to network interface. So, these interfaces are different because these interfaces, these UNI interfaces may be relatively slower in speed compared to the NNI interfaces. They can be relatively of much faster, much higher speed because of time division multiplexing being used. So, two different types of interfaces are specified in ATM architecture. One is UNI between user to network, and another is NNI between switches in the ATM network. And the communication take place by using virtual circuit, and there are three components involved in it. One is the transmission path. Transmission path is essentially the transmission media, that physical media that is being used while doing the transmission. On the other hand, the virtual path and virtual circuits, these two are two components with the help of which the virtual connections are defined. And the virtual path, essentially within each transmission path there are several virtual paths. For example, I can give you the example of two cities connected by highways. So, all the highways refers to the virtual paths. So, here you have got say one city, and here you have got another city. So, there can be several highways linking to it. So, this is your you can say that this link is the transmission path, and within each transmission path you have got virtual paths, VPs, several VPs you can have. So, this is your transmission path, and you have got several VPs inside. So, essentially all the VPs together form the transmission path between the city C1 and another city C2. And then within each virtual path you can have several virtual circuits. For example, a highway can have several lanes, 5 lane, 8 lane, like that. They form the virtual circuits within a virtual path. So, you find that this is the transmission path which which is essentially a physical medium between two nodes or between a user and a node or switch, and within this TP you will have several virtual paths, and within each virtual path there will be a number of virtual circuits. So, this kind of hierarchy is used for the convenience and it will provide a number of advantages, and these are the advantages of virtual paths. First of all, it simplified the network architecture. You can organize it in a hierarchical manner, and this leads to increased network performance and reliability, and it reduces reduced processing and short connection setup time. Because of this hierarchy, the connection setup time will be small, and the processing time also will be less, and also it enhances network services. So, these are the advantages provided by these virtual path concepts. So, let us look at the characteristics of virtual circuit connections. First of all, it has to provide some quality of service, that means delay, jitter, variation in delay, bandwidth, bus size. So, these are the quality of service parameters that is being these are has to be specified. Then the switched and semi permanent virtual channel connections. So, as we shall see, we shall have permanent virtual circuit as well as switched virtual circuit. We shall discuss about that. That is being supported by ATM. Then the cell sequence integrity. Whenever the packets travel through the same virtual circuits, the packets are delivered in order. As a consequence, the cell sequence integrity is preserved, and at the other end there will be no need to put them together in order. That means out of order delivery will not take place. Then the traffic parameter negotiation and users monitoring is also performed with the help of these virtual circuit connections. So, these are the typical characteristics, and the virtual connection is defined by a pair of numbers known as VPI and VCI. So, VPI stands for virtual path identifier and VCI stands for virtual circuit identifier. So, in case of UNI between the user and network interface, the VPI is 8 bit and VCI is 16 bit, and on the other hand between the two networks or switches, the VPI is 12 bit and VCI is 16 bit. So, that means as we can see, a particular virtual path is identified by 24 bit in case of user to network interface, and it has got 28 bit in case of network to network interface. So, that provides enormous number of virtual circuits to be created between an user and a network, and also between two networks, and obviously this number is much larger. And like X.25 and frame relay, ATM uses two types of connections. One is permanent virtual circuit and another is switched virtual circuit. In permanent virtual circuits, this is established by the network provider, and those numbers, that PVI, as I have mentioned, that VPI and VCI, these are all provided by the network provider in case of PVC. On the other hand, whenever in case of switched virtual circuit, this uses the services of the that ATM has got no network layer. So, it has to take the help of one upper layer. For example, internet protocol is a network layer protocol, that the ATM has to take the help of one network layer protocol to set up the connection and to establish connection, and that time those VPI and those VCI are defined. Let us see how exactly it happens. So, a setup signal goes, setup packet goes from one side to the another side, then the call processing message comes to this end, and then the signal connect comes to one end, and then connect acknowledge signal goes to the other end. So, that with this the connection is established, and that VCI and VPI are all defined, and then data transfer can take place. As you can see, data transfer is taking place from the from destination to source to destination between two end users, and after that the data transmission is finished, the connection is released, and the release connection signal is sent, and release completion signal comes from the other end, and with that ends the whenever a particular connection is set up in switched virtual circuit, this is how it takes place. That means the sequence of events that takes place in switched virtual circuit I have explained. Now, let us look at the different types of the switching types used in ATM. As we know, the switches are used to route cells from source to destination endpoints. So, it does routing and switching, and there are two types of switches are used. One is known as VP, another is known as VPC. So, routing is done using VPI for switching, the VCI remains the same. Usually between two switches, the switching is usually in the form of VP switch normally. That means routing is done only by using the VPI, the VCI remains same. For example, this is one interface, this is another interface, and this is a ATM switch. The packet is cell is coming to interface 1 and it is going towards the interface 4, and that this has already been set up. And now you see the VCI part 63 is same. So, it is not different, only difference is the that VPI part. So, VPI here is 75 at the input interface and the VPI is 83 at the output interface. So, the switching is done, it comes here, and used by looking at this table the VP switch identifies to to which port it will be assigned and what will be the VPI to be provided to that. So, the cell is forwarded in this form with the help of these two numbers. That means, the cell header will have that VPI VCI information, and with the help of that routing or forwarding will take place. On the other hand, in VPC switch, routing is done using both VPI and VCI, and usually the that UNI interface uses this kind of switching, and where both the that VCI and VPI is being used. And so, this is the cell arriving at the interface 1 with the VCI and VPI 78 and 83. VCI is 83 and VPI is 78, and it will the output will be forwarded to interface 4, and when it is forwarded, it assigns different VPI and VCI. So, VPI is now 93 and VCI is now VCI is 83, VPI is 78, here VCI is 93 and VPI is 68. So, we see, so it is being modified by the switch and then it is forwarded. So, by looking this kind of table, the cell switching and multiplexing is being done with the help of the switches. Now, you may be asking, this is how this is done by the hardware. It has to be done by the hardware, and you have to use some kind of switching fabric. One type of switching fabric that we have already discussed, that is your Banyan tree. Banyan tree. So, this is the Banyan tree shown, and here it is shown, it has got 8 inputs and 8 outputs. So, 8 input and 8 output lines are being shown here. So, as you can see, the cells are arriving here and it can go to any one of these lines. So, directions are shown in a different, actually these are output lines and these are the input lines. So, whenever it comes to 1, it can go to any one of the output lines and it is being buffered. So, these are buffered here, you can see each line can have input and output. Actually, it can be full duplex, it has to be full duplex. Here it is coming, then 0 to the 0 interface, it can go to any one of the interfaces, and then this switching is done with the help of these bits. So, inside it has got micro switches. So, these micro switches are used to do the switching. That means, depending on this bit, depending on this 1 or 0, the input will go to this end or this end. Obviously, at a time it will be able to switch one of the two inputs either to this or to this. So, if they want to go to the same output, then what will happen is known as collision. So, whenever the destinations are different, even then this collision can occur. However, the switching can be done in this way with the help of different bits. For example, if the destination is 6, then it goes that input, say from 1 it has to, say let us take from 0 it has to go to 6. So, from 0 this bit is 1, so it will go here this path, and see this 6 is 110. So, again it will go here, then it is 0, so it will go here. to this particular output line. So, in this way the switching done, however, collision can occur. So, with the help of whenever it has got n inputs, a Banyan tree switch will have log 2n stages. So, here the number is 8. So, it will have 3 stages as you can see, and in each stage there will be about n by 2 switches, micro switches. So, n by 2 is 4, we have got 4 micro switches and 3 stages in this 8 by 8 switch. Unfortunately, as I mentioned, because of internal collision, even for different destinations coming from different input sources, there can be internal collision. That internal collision can be avoided by using which is known as Bacher-Banyan switch. So, what is that? It combines 3 different modules. One is the Bacher switch. What the Bacher switch does, whatever input it receives, it does the reshuffling. How? In terms of the output port, output link to which it is going. That means all the inputs are reshuffled based on the destination lines. So, this Bacher switch does that, and unfortunately there is a possibility that some of the cells coming from some of the inputs may have the same destination port, destination line. So, in such a case it cannot be sent simultaneously to the Banyan tree. So, this is being overcome by using this trap module. So, trap module will buffer them, then per tick one cell will be forwarded to the Banyan tree. So, in this way the Bacher-Banyan switch can perform the ATM switching, and it overcomes the limitations of the simple Banyan tree, and this kind of switching fabric can be used in implementing the ATM switches. Now, let us look at the different layers used in ATM. As I mentioned, ATM has got 3 different layers: physical, ATM and ALL. ALL stands for application adaptation layer. So, physical layer defines the transmission medium, usually it is optical fiber, bit transmission encoding and signal conversions. So, it may be necessary to convert from electrical to optical and optical to electrical. So, physical layer does that. So, this was originally based on SONET. That means, we have already discussed about the synchronous optical network. ATM was based on SONET, and as we know, that in case of ATM the lowest rate is 155.52 megabits per second. So, this is the minimum bit rate, and it has got higher rates. So, with provision of, however, the ATM can not only use SONET, it has the provision for other technologies. That means, it can use it may also use the T1 lines if necessary, but it has been explicitly designed for SONET. Then the ATM layer performs routing, traffic management, switching and multiplexing. So, the ATM layer performs the important function of routing, traffic management, switching and multiplexing. On the other hand, the ALL layer, application adaptation layer, accepts frames from an upper layer protocol and maps them into ATM cells. That means, the packets or frames coming from different applications, they may be of different sizes. The ALL layer does the mapping to the ATM cells. That means, it will break them up, segment them, and also it will do the combination. Let us see how it is being done. And here the functionality of nodes and stations are defined. As you can see here, the functionality of the user stations has got 3 layer functionality: physical, ATM and ALL, application adaptation layer. On the other hand, the switches has got only 2 different layers: functionality of two different layers, ATM and physical. So, all the switches have got ATM and physical layers within this ATM network. Only the user interfaces has got 3 layers of functionality: physical, ATM and ALL. And here it shows the functionality of different layers and how it actually happens. So, here the information stream is coming from upper layer. The ALL layer does the segmentation of the frames, so in terms of 48 bytes. So, it breaks it in terms of 48 bytes, and the ATM layer puts the header, converts it into ATM cells, and that it has got it introduces that 5 byte header. So, with that it gets converted into cells each of 53 bytes, and then it passes through SONET layer, and we have already discussed about the SONET layer. As we know, the popular ones are 12C and 3C, which is commonly used for ATM, and as we know the data rates are 155.52, and for 12C it is 622.08 megabits per second. And of course, there is as I mentioned that T1 lines, that DS3 protocol can also be supported, but primarily it uses these two. So, here it is explained with the help of this SONET 3C. So, SONET STS 3C, this is the frame. So, in this frame, as we know, we have got the packet overhead header, then SONET overhead header, line overhead header. So, these headers are there. So, 9 bytes and then 1 byte for this is 1 byte for the packet overhead, and remaining are used to pack the ATM cells. So, as you can see, 9 into 260 byte, this is the SPE, this is the synchronous packet, and in this the ATM cells are packed, and with this we can have 44 ATM cells can be packed in this. And here that 5 byte header that is being added by the ATM cells are elaborated. So, it has got two different types of headers for UNI, user to network interface, and network to network interface. Main difference is coming from this GFC. GFC is the generic flow control. This generic flow control it was assumed to be between the user and here is your ATM network between the switch. So, this flow control was assumed to be used between the user and the network, and that is why 4 bits were left aside by the designer of ATM. However, this is not commonly used. So, we may consider this GFC as a flaw in the design. So, it is not commonly used. Then VPI, that virtual private identifier, is 8 bit, as I mentioned, between the user and the network layer for UNI. On the other hand, it is 12 bit for the NNI interface. So, whenever it is between two switches, for that it can be 12 bit VPI and 12 bit VPI and 12 bit 16 bit VCI. So, VCI is 16 bit for both cases. Then the payload type, it has got 3 bits. That payload type specifies what kind of payload a particular cell is carrying. So, this is the meaning are explained here. For example, if it is 000, the most significant bit specifies whether it is user or management data. So, if it is 0, then it is user data, but again user data can be of two types, type 1 or type 0, depending on the least significant bit, and the middle bit is used to specify the conjugation. So, whenever it is 000, it is user data, that means that cell corresponds to an user, and there is no congestion in the network, and it is a type 0 type payload. On the other hand, whenever this bit is 1, it is user data, no congestion, and in type 1, and whenever this bit is set to 1, user data congestion has occurred in the network and type 0, and whenever this is 1, it is type 1. When this is 100, it is a maintenance information between adjacent switches. That means the two switches can exchange some information, and that management information is specified with the help of this payload type 100. On the other hand, this maintenance information can be between source to destination. So, between source and destination, in that case it can be the payload type is 101, and this 110 when this payload type is used for resource management, and 111 has been left for future. So, this is your payload type, and CLP essentially provides you cell loss priority. There is only one bit specifies for that cell loss priority, and the cell loss priority specifies is used for congestion control. As we know, whenever congestion occurs, it may be necessary to discard packet, and that is done with the help of this payload type bit. Whenever it is 0, whenever it is 1, whenever this payload type bit is 1, that means packet is of higher priority, and whenever it is PT is 0, this is the cell is of lower priority. That means when congestion occurs, the cells with PT is equal to 0 can be discarded, and as long as cells with PT is equal to 0 are available, only those cells are discarded. That cells with PT is equal to 1 are not touched. However, whenever congestion is high, that time these cells may be discarded. And this there is 8-bit header error control. We shall discuss about it in more detail. So, this header error control, it is a 8-bit field, and the characteristic polynomial that is being used is shown here, x to the power 8 plus x square plus x plus 1. So, this is being used for error detection and control correction. As you can see here, normally when there is no error, it is in correction mode, and whenever there is error, it goes to detection mode. So, whenever you have got single bit error, then it can be corrected. As you can see, whenever there is single bit error, it can be corrected, then it goes to the detection mode. And on the other hand, whenever it has got multi-bit error is detected, then the cell is discarded because it cannot be corrected. That means each switch does the error checking. So, it will have some overhead, although it is done by hardware, and whenever there is single bit error, it can be corrected because it uses 8-bit for error correction purpose, and it does the error correction only for the header part. That means the previous 8-bit, we have seen that here you have got how many bytes? 1, 2, 3 and 4. That means on these 32 bits or 4 bytes, error correction is done, and this code is that CRC check bits are kept here. So, HEC operation is performed at the receiving end for error correction purpose and error detection purpose. Now, the nodes make use of fixed cell size and HEC to determine the cell boundaries implicitly. One important feature of cell switching is that there is no flag bits to identify the beginning or end of a cell. So, how a cell can be beginning or end of a cell can be identified? That is also being done with the help of this header error control bits in an implicit manner with the help of cell boundaries. That state transition diagram used for that purpose is shown here. Normally, the switches are in the hunt mode, then it checks in the bit by bit synchronization is done, and whenever correct HEC is header error correction is received, then it does cell by cell checking. So, it is in a pre-synchronization phase, and whenever it receives not several consecutive header error controls correct HECs, then it is goes to synchronization mode. That means usually this value of B is not less than 6, usually 5. So, if you keep it 5, that means 5 cells are received correctly, that means header error corrections is correct, then it goes to synchronization. Then each and every cells are now synchronized with the help of this header error correction, and then as the cells arrive with 53 byte, once it gets synchronized, then all the subsequent cells are synchronized. However, whenever there is incorrect header error controls, it must have consecutive 7 less than 7 consecutive incorrect header error control flags are received, then again it goes back to the hunt mode. So, we find that the cell delineation is performed with the help of the header error control bits, and synchronization is done with the help of this particular field in an implicit manner. Now, ATM supports a number of service categories, and these are divided in 5 different classes. One is constant bit rate, for example, it is coming from the telephone network T1 circuit. So, it comes in a constant bit rate. On the other hand, the second type is variable bit rate, and it is of real time. So, say real time video conferencing, or it may be coming from it may be video data, and it is coming in a streamed form without any compression, then it is real time video or audio data it can be. On the other hand, whenever it is real time, it is non-real time, variable bit rate non-real time, say for example multimedia email, then it can be variable bit rate non-real time. On the other hand, available bit rate, browsing the web is the application, whatever some minimum bit rate is specified. However, if higher bit rate is available, that is being used, that is used in the applications like browsing the web, when you are browsing the web. And then unspecified bit rate, so the no specific bit rate is specified, whatever bit rate is available, UBR, that is unspecified bit rate, that can be used for background file transfer and other purposes. So, real time video conferencing is going on. In addition to that, you can do background file transfer with unspecified bit rate. So, these are the different types of service categories identified by ATM designers, and accordingly the ALL layer frames are it has got different types of 5 different types. For example, that ALL layer has got all the originally 5, now it is divided into 4 different types. For example, ALL 1 is for constant bit rate stream, and ALL 2 for short packets coming from say video or audio applications, ALL 3 or 4 for conventional packet switching, and ALL 5 for packets not requiring no sequencing and no error control. That means for simple applications, when sequencing is not required and error control is not required, this particular framing can be used. And this ALL layer is divided into 2 parts. One is that CS sublayer that perform convergence sublayer and segmentation and reassembly sublayer. So, these 2 functions are different. It performs, as I said, it has to perform segmentation and reassembly, and also it has to perform the convergence. So, let us look at the 4 different types of ALL frames that is being used, how it is being done. So, this is being used for constant bit rate stream, as I have already mentioned. So, you have got constant bit streams are coming, and the CS layer has got it divides it into 47 byte packets, and that SAR sublayer, that segmentation and reassembly sublayer, puts an header which has got 2 fields. that SN and SNP sequence number and sequence number protection, that means for checking purposes. So, these 8 bits are used as header in the is added, then it goes to the ATM layer which forms that 55 bit cell with 5 byte header, and I have already discussed about this 5 byte header. Then it is transmitted to the network. On the other hand, in case of ALL2, which is used for low bit rate and short frame packets such as audio, video and fax, as I have mentioned, the packets are smaller in size, say 24 bytes. So, to make it 47 byte, you have to add a pad. So, here as you can see, the segmentation and reassembly header is little different, having different fields like LI, PPT, UI and HFC. I am not discussing all these details, and that SAR header is SF. So, you see 2 headers are added, the CS layer puts a header, the SAR layer puts a header, here it is 3 byte CS layer and here it is 1 byte, and remaining part is filled up with pad. So, to make it 48 byte altogether, which goes to the ATM layer, and ATM layer puts the header 5 byte header and sends it through the switches. And here that ALL 3 and 4, which are used both for conventional applications with which can support both connection oriented and datagram type applications both, and here you see the data packet up to 64 kilobytes can be supported, and as you can see, data is divided into packets by the ALL layer. So, each with say header and tailer. So, header and tailers are added, and this 44 byte payload are taken from the upper layer, and then it forms the 48 byte cell which goes to the ATM layer, which forms the 53 byte cell, and that is being transmitted through the network. And then ALL5 simple and efficient adaptation layer. As you can see, this is the frame format. Here also the data packets are up to 64 kilobytes, and here as you can see, there is no sequence number, no sequencing and flow other control, flow control is needed, and that is why this is known as simple and efficient adaptation layer, where there is no header or tailer, no error control or segmentation is done, I mean sequencing is done, no sequencing, no error detection is performed. That goes to the ATM layer, and which forms the packetization, then it sends it. And let us see how congestion control is performed in ATM. Since conventional congestion control schemes are inadequate for ATM because of the following reasons: the majority of traffic is not amenable to flow control because it uses real time traffic, where you cannot enforce flow control. Feedback is slow due to reduced cell transmission time, because the that propagation time is longer than transmission time. So, feedback is slow, relatively slow. Variety of applications supported by the ATM networks, as I have already mentioned, there are 5 different types of packets are transmitted, and very high speed of switching and transmission. Because of this, the conventional congestion control cannot be worked, and congestion control performed in 3 different ways. Admission control, when a station wants a new several techniques are used. Admission control, when a station wants a new virtual circuit, it specifies the traffic to be offered and services expected. If the network is unable to offer the service without adversely affecting the existing connections, the cell call is rejected. So, as we have seen, a particular circuit may not be allowed to set up. Then resource reservation is done. So, a setup message is earmarked bandwidth along the line traverses, and the bandwidth available is measured and which is being used. Then rate based congestion control is performed, where after each k data cells a sender sends a resource management cell I have already mentioned about that, and as it gets back to the center after reaching the destination, comes back to the center, it comes to know the minimum acceptable rate. So, now it is time to give you the review questions. Why are the benefits of cell switching used in ATM, or rather what are the benefits of cell switching used in ATM? What are the relationship between TPs, VPs and VCs? Second question. Third question is, how is an ATM virtual connection identified? Fourth question is, how cell boundaries are performed in ATM? Fifth question is, how congestion control is performed in ATM? Here are the answers of lecture number 23. First one was, in what layer X.25 operates? Answer is, X.25 operates in the network layer. Second question was, what are the key functions of X.25 protocol? Answer is, key functions of X.25 protocol are: call control packets are used for call setup, as we know. Multiplexing of virtual circuit takes place in packet layer, and both link layer and packet layer performs flow control and error control, as we have discussed in detail. Third question was, what limitations of X.25 are overcome in frame relay protocol? Answer is, in X.25 overhead on the user equipment and the networking equipment is very high, and it is also slower, which are overcome in frame relay. As you have seen that X.25 can go up to 64 kilobits per second, and frame relay minimum rate is 1.544 megabits per second. So, it is much faster and lesser overhead. Fourth question was, distinguish between permanent virtual circuit and switched virtual connection used in frame relay. In permanent virtual circuit connection, the path is fixed and data transfer occurs as with virtual calls, but no call setup or transmission is required. On the other hand, in switched virtual circuit connection, the path is dynamically established virtual circuit using call setup and call clearing procedure, and many other circuits can share the same path, as we have already discussed in detail. Fifth question and the last question was, how congestion control is performed in frame relay network. As we have discussed in detail, it uses 2 bits for congestion control: backward explicit congestion notification and forward explicit congestion notification, these 2 bits. In addition to that, it does the packet discarding. If users do not respond to congestion notices, packets are discarded by the switches. So, with this we come to the end of today's lecture on ATM and also the applications of packet switch networks. So, frame X.25, frame relay and ATM. Thank you.